So I will present a paper called Calibrating Multi-Class Models, written by Ulf Johansson, myself, and Henrik Boström. And the layout of the presentation follows basically the paper, and I will focus mostly on the results from the decision trees and only give a brief summary of the results from the random forest and XGBoost. But let's dive into this. So when having a classifier, we can that predict a label, we can make them assign an algorithmic confidence to them as well, which will increase a user's appropriate trust in the prediction. We then get what is called a probabilistic predictor, which sort of return a probability distribution over all the possible labels. And if these probability distributions are well calibrated and sharp, this can sort of increase the appropriate trust by the user, since that will sort of reflect the true underlying probabilities. Most machine learning algorithms can produce some kind of sort of confidence measure. However, it's too much to call them probabilities. So generally they are called just probabilistic estimates. And there are a number of techniques that we can use to calibrate these probability estimates. And the most well-known are Platt scaling and isotonic regression. However, they are only directly applicable to two-class problems. So when working with multi-class problems, you need to sort of work around this limitation somehow. And this has been tried, for example, using one versus all or all versus all schemes before you perform the calibration for each class, and then you sort of aggregate the different probability estimates or the calibrated probabilities together again. There are a number of drawbacks with this. And first of all, of course, you have to train a number of models. So instead of just having one model, you will need to train as many models as you have classes. And if you are using or you want to use interpretable model, there is no longer sort of one model to interpret. So instead you have to interpret all of them somehow, and it's basically very hard or not possible. So what we suggest in this study is a way of sort of calibrating multi-class models, and we only look at models that are sort of inherently multi-class, which means that they are able to not just predict the label, but also provide a confidence estimate for each of the possible labels. So what we propose in this study is that instead of sort of trying to assign a probability estimate for each of the labels, we instead treat the predicted label as our positive class and all other labels as our negative instances. And by doing that, we make it possible to use all of these calibration techniques that are only applicable to scoring classifiers. And the scoring classifier is a sort of binary scoring classifier. So it only produces scores for sort of the probability of predicting one, basically. And there is sort of or one obvious sort of benefit of our solution is that it provides the user with sort of a natural way of understanding the model as sort of an estimate of whether the prediction is correct or not. So we get a calibrated probability of whether each prediction is correct or not. So when talking about probabilistic predictor, they output both the label and the probability distribution over the labels. And sorry. And if this sort of predictive probability distributions, if they are performing well against statistical tests that we make, they can be considered valid. However, validity in this case cannot be achieved for probabilistic predictions, which has been shown by Bob and others. So instead of focusing on validity in this paper, we look at calibration. And calibration is the probability of a class given a probability estimate for that class should be equal to the probability estimate of that class. So basically, our probability estimate should be accurate, so to speak. Sorry. Platt scaling, as I mentioned before, is one of the calibration techniques that exists, and it fits a sigmoid function to the scores. And it's done using this formula. So given we have probability scores from the calibration set and a probability score for our test instance, then we can use this function to calibrate the probability, the calibrated probability of predicting a class. So this PC given S is the probability that an instance belongs to class C given its score S. And we have some parameters here which are found using a gradient descent search. Venn-Abers predictors Venn predictors are probabilistic predictors that sort of try to circumvent this impossibility result regarding the validity that I mentioned, or that Bob has shown, and they do it in two different ways. So once they restrict the statistical test for validity to calibration, and the second one is that they output multiple probabilities for each labels. So and where only one of them is the valid one. So basically, it outputs sort of what we interpret as an interval for each label, but only one of them is the correct probability. A Venn-Abers predictor is a Venn predictor, and a Venn-Abers predictor sort of improves on Venn predictors in the way that they can automatically optimize the taxonomy, and they do that by using an isotonic regression. And an isotonic regression or an isotonic calibrator is a stepwise non-decreasing regression function. The benefit of Venn-Abers predictors being Venn predictors is that they also inherit the validity guarantees given by the Venn predictor. But since the Venn-Abers predictor uses an isotonic regression, they can only be applied on binary problems, so they can be applied on scoring classifiers onto which they produce multi-probabilistic predictors with these unique validity properties. So the way that we can create multi-probabilistic prediction from an inductive Venn-Abers predictor is by following these steps. So first of all, we have a property or a training set where each instance in this set consists of an object and a label. And then we divide this set into a proper training set and a calibration set. We train a scoring classifier using the proper training set. And then we use this scoring function or scoring classifier to produce prediction scores S0 and S1 for our new object, our test object. So these are sort of the probability estimates or prediction scores for class 0 and class 1. Then we build two different isotonic calibrators, one for the 0 class and one for the 1 class. And the output of this procedure is the probability interval for that the label is 1. And this probability interval is given by, we get by applying this 0 isotonic calibrator on the test object to get the lower bound, and then the class 1 isotonic calibrator on the test object to get the upper bound. In our study, we have used 3 different kinds of underlying models. So we have used decision trees, random forest, and extreme gradient boosting techniques. Decision trees are greedy divide and conquer models that build sort of a decision tree structure or tree structure. When they are producing probability estimates, they are generally called probability estimation trees. And we have been using the decision tree classifier in scikit-learn. Random forests are ensembles of what is called random trees. And the random tree is a kind of decision tree, but instead of training on all the data, we are using a bag of data which has been sort of drawn randomly with replacement from the proper training set. And then also when deciding each internal split, we are using only a random subset of the available attributes to choose that split. And we have used the random forest classifier in scikit-learn for this study. And the probability estimates in that technique is the mean predicted class probabilities of all trees. I forgot to mention that the probability estimate for a pet in scikit-learn is the relative frequency. Finally, the extreme gradient boosting is a highly scalable implementation of gradient boosting, and it improves a lot of improvements on the original algorithm. And it uses the same kind of calculation to get the probability estimates as the random forest classifier. So when we apply our model, we first train the underlying model using the proper training set. Then we apply it on the calibration set to get the confidence measures for each label. And then when we get a new test instance, we also produce a probability estimate for that object. And then we use the predicted or the probability estimate for the predicted class as the probability estimate for the positive class, and then all the 1 minus that as the probability of all the other classes. And then once we have sort of turned our problem into a binary problem, we can apply any binary calibrator onto our problem. So we can use Platt scaling and Venn-Abers, for example. So when we're using Platt scaling, we only need to do calibration once for each label, of course. But when we're using Venn-Abers, we need to do 2 calibrations, one for the lower bound and one for the upper bound for each test instance. And we then have to sort of transform this lower and upper bounds into one probability estimate, and we do that by regularizing the interval in the following way, as you can see in the equation here. When doing calibration on multi-class normally, we would of course need to train at least C models where C is the number of classes. So we would need to train more models than we need to do in, or more calibrators than we need to do in our solution, of course. The three different setups that we have evaluated is, first of all, not using any calibration. And to sort of get a fair comparison, since that solution doesn't need any calibration set, we have used the entire training set to train those models. So we haven't put aside a calibration set for this model. So it uses more data than the other models. When using Platt scaling and Venn-Abers, we have used the proper training set, so only a part of the training set to train the model, and then we have a calibration set on which we do the actual calibration. So as I said before, the label predicted by the underlying model is the positive class, and this is true for both of these both Platt scaling and Venn-Abers. And however, when working with Venn-Abers, of course, we have to sort of augment the test instance with both the negative and the positive class. But we always sort of treat the predicted label as the positive class and not the positive label as everything else, so the negative class. As I said, scikit-learn has been used, and with default settings, except for the mean sample leaf in the decision trees. And this has been set to 4, which means that each leaf must contain at least 4 training instances to have some kind of substantial number of instances to calculate the relative frequency on. We've used tenfold cross-validation, and we have divided the training set into the proper training set 2/3 and the calibration set 1/3. And as I said before, all the training data was used to generate the non-calibrated models. We have used accuracy and area under the curve for to evaluate predictive performance. And when evaluating the calibration quality, we have used the log loss and the expected calibration error. Yeah, I think I will just move on. We have evaluated on 20 publicly available multi-class datasets from the UCI repository, with some variation in size and number of classes and number of features and so on, but these are sort of fairly small datasets. So the results finally. So this is an example of a decision tree where we have applied this technique. So what we see here is a tree where we have actually changed this mean leaf size a little bit to make sure that we can fit the final tree into our presentation. So in this example, we actually have much more instances in each leaf node than just the minimum 4. So in this 7-class problem, we have ended up with 7 different leaf nodes, 1 for each class. And as you can see, we have fairly tight intervals for each of these leaves, but we also have these intervals, and we have we have intervals for each class, even though it's not a binary classification. And in this particular example, these high probabilities actually were 100% correct in both of these cases, and the other ones were sort of fairly accurate as well. Of course, when looking into an individual tree, you will also always have some sort of statistical fluctuation. So, but the sort of calibration works in the long run, so to speak.
5 minutes.
Sorry?
You have 5 minutes still.
Okay, yeah, thank you.
Thank you.
So this is how it looks when sort of predicting using the ensembles. So we get the probability estimate for the prediction, and we can then see that in these cases, mostly when we have high probabilities, it's correct, and mostly when it's low, it's incorrect. So I will move on then. These are the results for the decision trees, and these are for accuracy in AUC, and as expected, when using more training data, we will get better results when looking at accuracy and area under the curve. So these results are expected. However, when looking at the some of the data sets, so this is a typical example from a decision tree where the underlying model is really overconfident. So most of the predictions are really having really high probability estimates here, whereas both of the calibrated probabilities are much lower, as we can see. So in this case, we have managed to increase or improve the ECE quite a bit. This is not a very typical data set for the decision trees, but even in this case, when we have when the underlying model is fairly well calibrated to begin with, both of the calibration techniques manages to sort of improve the calibration by lowering the probabilities for the high predictions. When looking at the log loss and ECE, we can see for the log loss, we can see a huge difference. So it's obviously very much better to use these calibrated probabilities. We also see a huge difference for the ECE. And of course, this has to do with how a decision tree works, where we sort of yeah, sorry, I will just move. So while so most of the decision trees are really poorly calibrated, and generally they are very overconfident. So by using these calibration techniques, we are able to reduce or sort of improve the calibration quite a bit. But of course, at the cost of having lower accuracy in AUC, since we can't use all the data. When looking at the Venn-Abers and XGBoost, I will only present the summaries. But here we can see again that the underlying models will be better when we can utilize all the training set, of course. And there is not much difference between the calibration techniques regarding both of these measures. When looking at the Venn-Abers, they are generally underconfident as opposed to the decision trees. But the calibration by Platt and Venn-Abers are able to sort of handle that and increase the probability estimates for these models. And on the other hand, the XGBoost is just like the decision tree; they are overconfident, and again, Venn-Abers and Platt scaling can sort of handle that and reduce the probability estimates. So when looking at the log loss and ECE, we can see a huge improvement regarding ECE, not as large as for the decision trees, but still much larger. The difference on log loss is not as big, but one reason is, of course, that in the decision trees, in the leaf of the decision tree, we don't have this granularity, so there can be a lot of different instances that fall into a leaf. Whereas both the random forest and the XGBoost are able to sort of create a much more granular probability estimate fitting, so to speak. Okay, and then the summarizing of, so we see basically that when applying the calibration techniques to the underconfident random forest and the overconfident XGBoost models, they are quite successful in handling the calibration. And of course, again, the loss is lowered predicted performance by the models. One interesting thing, the final thing, is the prediction intervals for the Venn-Abers predictors. So for the different techniques here, we see that most often the accuracy of the model falls within the average of the low and high bounds, especially for the random forest and the XGBoost. Again, for the decision trees, it's the same reason. We see more errors here, but it's again for the same reason that they are not as granular in their predictions, so to speak. So they only have they have much fewer number of predicted probability estimation levels, so to speak. So conclusions. So we have proposed a novel approach for applying or calibrating multi-class models. So instead of trying to get the probability estimates for all of the possible labels, we only provide a probability estimate for the model being correct in its prediction. Which means that we can use all the normal calibration techniques even for multi-class models. And we have evaluated this approach on 20 data sets using decision trees, random forest, and XGBoosts. And we can see that it works regardless of whether the underlying model is overconfident or underconfident. It works quite well, actually. And Platt scaling and Venn-Abers were sort of comparable, except for when working with pets, where Venn-Abers were clearly better. I also have some future work, but I think I will skip that since my time is up right now. So thank you very much.